Hello, I am Viphretuo. I am a PhD student at the Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore, India. The title of my presentation is Silicon Photonics Enable On-Chip Optical Readout of PiezoMEMS Resonators. We know that MEMS devices are highly attractive because of its wide range of applications. To name a few, they are used in mass spectroscopy, biomolecular sensing, atomic force microscopy. The reason for its popularity is because MEMS devices can be tailored for high sensitivity towards various external stimuli, and one such device is the MEMS-based microcantilever that is widely explored for various sensing applications. The operation of a cantilever is usually done in two modes. In the static mode of operation, the response of the cantilever to external stimuli results in a change in the tip deflection. In the dynamic operational mode, the cantilever's response to an external stimulus is captured by a change in the vibration frequency. For instance, when molecules absorb on the surface of the cantilever, they induce differential stress on the cantilever and causes the cantilever to bend in a particular direction. At the same time, because of the mass loading effect, the vibration frequency also shifts. So, to record these outputs, typically electrical or optical based readout methods are used. In electrical based readout technique, the measurable output is in the form of a change in current, which is produced by a piezoelectric or a piezoresistive element that is embedded on the cantilever. Although electrical readout offers low cost and chip scale integration, it suffers from poor sensitivity because of the thermal noise. On the other hand, optical readout technique offers better displacement resolution. However, conventional optical detection schemes are bulky because of the use of free space interferometers and laser deflection systems that is used to record the mechanical motion. For example, the figure on the left shows a laser Doppler vibrometer that is used to measure the cantilever vibrations. However, the system is quite bulky, as we can see that. Therefore, this limits conventional optical readout technique for application which requires portability. This problem can be solved by taking advantage of photonic integrated circuits. Photonic integrated circuits offers the integration of different optical components and optical functionalities on a single chip. The figure on the right shows a grating sensor which uses a photonic grating to probe the cantilever vibrations. Here, the grating sensor consists of an input and output grating that is used to couple in and out light into the chip, and the waveguide is used to route light across the circuit. And here, the interrogation grating is directly beneath the cantilever, which is used to probe the cantilever vibration. And compared to a conventional laser Doppler vibrometer, the grating sensor offers increased alignment tolerance as both the grating and the mechanical resonator can be integrated on a single chip, and it can be defined using lithography. And also by taking the advantage of CMOS fabrication, it can also be mass produced. So the grating sensor works on the principle of interference. So light is coupled into the chip using the input gratings, and when the guided light interacts with the interrogation grating, light is diffracted at an angle theta. And after reflection from the top and the bottom interface, light recombines back with the two other waves. So when the cantilever moves, the upper wave accumulates a phase with respect to the other two waves. So when the phase difference is pi, or when the phase difference is 0, it results into a destructive or a constructive interference. So as shown in the figure below, the transmission of the grating sensor is maximum when there is constructive interference, and when the transmission is low, that means that there is a destructive interference. Therefore, the cantilever vertical motion causes modulation of the input signal, which can be measured at the output using a photodetector. This grating sensor has been explored by different groups, and recently the grating sensor has been used for highly sensitive on-chip optical readout with picometer scale resolutions. And here in the figure, the limits of detection is quite comparable to the conventional optical readout system. However, in these devices, as we can see that the mechanical structure is built on top of the interrogation grating. Therefore, this limits the choice of material that can be integrated or it can be used for the mechanical resonator. For instance, if you want to integrate an exotic material such as PZT, which is a piezoelectric material on top of the cantilever, the fabrication can be quite complex. Therefore, in this work, we provide a scalable approach where both the photonic chip and the mechanical resonators are fabricated separately and later integrated via a bonding approach. As a proof concept, here we demonstrate the bonding of the interrogation grating and a PZT-based microbeam. The figure on the left shows the schematic representation of the flipped PZT beam that is bonded on top of the photonic chip. To avoid collapsing of the beam prior to the bonding, a trench is created by depositing 5 micron thick silicon dioxide followed by lithography and etching. And after bonding, we have used an optical profilometer to measure the gap between the beam. Here, the profile shows that the total height is about 34 microns, but the total thickness of the beam is about 26 microns, so which gives us a gap of about 8 microns. Here on the figure on the right shows the optical microscope image of the device under test, and the electrical probes are used to actuate the beam, and the alignment markers are used for the correct placement of the beam on top of the gratings. The frequency response of the device is captured by applying a sinusoidal voltage to the PiezoMEMS resonator. For the optical readout, light from a tunable laser is coupled into the chip via the input-output grating couplers using the single optical mode fiber. Here, a polarizer controller, which is PC as indicated, is used to control the polarization of the light. And the modulated light is captured at the output using a high-speed photodetector, which is connected to a lock-in amplifier. The figure on the left below shows the frequency response of the beam as obtained from the on-chip optical measurement. The 3 peaks corresponds to the first, second, and third vibrational modes of the beam. And to verify the vibrational modes, we have used a laser Doppler vibrometer. And the figure on the right shows a comparison of the fundamental mode as measured using on-chip vibration measurement and laser Doppler vibrometer, and they are in good agreement. And the figure instead shows the mode shape of the fundamental mode. So to improve the quality factor, we have also done the on-chip measurements in vacuum by applying the same drive voltage. Here, the measurement in vacuum shows 1 order improvement in the Q factor because of the reduced damping. Further, we also observe a shift in the resonant frequency when the measurement is performed in vacuum because of the reduced damping. Therefore, in summary, I have presented the integration of silicon photonics based on-chip optical readout and PiezoMEMS devices. The integration strategy allows independent development of photonic and MEMS chips. And finally, the configuration can be exploited for a variety of sensing applications that uses mechanical resonators. I would like to acknowledge my collaborators, the funding agencies, and my team members for helping me in this work. Thank you for listening.